So this video goes over the end of class on December 7th. This goes over particle representations and BCA tables. So you got 10 minutes to look at the PhET simulation and to play the level 1 game. That's good, good practice for looking at particle models. So we can take the particle model of reactants and draw what the products will be based on what we see in the reactants and also relate it to the balanced chemical equation. So first, let's balance this. This would be 1, and then this would be 3, and this is 2 to balance the reaction. Here in scenario 1, we have the exact ratio that's shown in the balance reaction. We have this is our N2, so we have 1 N2, and we have 3 H2 molecules. So we can tell that because it's a 1 to 3, 1 to 3 here, we should end up with 2 ammonia molecules here. We can also tell this from the fact that we have 2 nitrogen atoms, so we could put those into ammonia molecules. And so our particle diagram for the products would be 2 ammonia molecules as we would predict from the balanced chemical reaction. Here here nitrogen is blue and the white circles are hydrogen. Now here again, in these reactants, this time we have 3 N2s and we have 9 H2s. Again, here we have the correct exact ratio in a 1 to 3 relationship. 3 to 9 is the same as 1 to 3. So taking a look at this, right, if we start off with 3 N2s, 9 H2s, we will get twice as many NH3s as N2, right? The ratio between N2 and NH3 is 1 to 2, and we have the exact number of hydrogens, 1 to 3 ratio, to react all of those nitrogen molecules. So here, to draw our particle model here, we want 1. We're going to make 6 ammonia molecules. I'll put in all my nitrogens first, and then put in the hydrogen for ammonia. So here we have formed 6 NH3s. And we can see that this is the exact ratio shown in the balance reaction, 1 to 3 to 2, same here. 3 to 9 to 6 is the same as 1 to 3 to 2. This is the exact ratio. We should also be able to go from the products and predict what the reactants were based on the products that we're seeing. So if we see 2 ammonia molecules here, okay, that means this must have come from, based on the balance reaction, this must have come from 1 and 2 and 3 H2s. So we can draw those particles here. We can draw 1, 2, 3 H2s and 1 N2 molecule. So hopefully just from conservation of mass, you can see this relationship playing out in the particle diagrams, but also you can see this conservation of mass and the ratios in the balanced chemical reaction. Another way to represent this reaction, okay, here we have again our 3 N2s plus our 9 H2s forming 6 NH3s. We're going to be using something called a BCA table to represent the what is happening in a chemical equation, in a chemical reaction, before and during and after it proceeds. This before line is what the reactants show. Okay, so the reactant box here is represented by the before. this change, it's what's used, okay? And the after is the products. So here I can, based on my images, right, for the reactants, I can put in 3 and then 9 and 0 initially, right? Before the reaction, there are no ammonia molecules. What's used? Well, we have to use 3 nitrogens. We have to use 9 hydrogens, and that produces 6 ammonia. So this is what's happening during the reaction. And you can see that our reactants right here, let me put a sharp dividing line between the reactants and the products, right? These disappear, so they're minus, they're used up, but the products up here, so that's a plus sign. So here now all of these are used up in the product, and we have 6 ammonia particles left in the products right here. Now, I apologize. I should not have picked this ratio for the next one, but here we're still okay here. Here in scenario 3, okay, in real life, we don't usually have the exact ratio like this, where we have that exact 1-to-3 ratio so that we don't have any reactants left over. Things rarely react in a way that we have exactly 1-to-3 here for the ratio, or whatever ratio of the reactants we're supposed to have. So rarely do we have 0 for both of the reactants. And so here in real life, we usually don't get the exact ratio. Okay. And so in scenario 3, we have a situation here where we have 2 N2s plus 8 H2s and so we don't have this 1-to-3 ratio. Instead, we have a 1-to-4 ratio. So we know that we're going to have something left over. One of these reactants will be left over because we're not in the exact ratio that we should be in. Okay, so here, if we react away these 2 N2 molecules, right? If we have 2 N2, then we should use 3 times as many H2s, right? If 2 N2 is completely reacted, okay, we should have 6 H2s. Okay, if 8 H2 is reacted, okay, then in that case, right, we should have a third of 8 N2s, a third of 8/3 N2, which I apologize for picking this number because I should have picked something more even. So what I'm going to do is, to make this next part and this a little bit more understandable, I'm actually going to draw in another hydrogen molecule. But for now, we can see that if 2N2 is completely reacted, we need 6 H2s. And if we look here, we've got 8 H2. We have more than enough. So we call N2 something called the limiting reagent or limiting reactant. And then H2, since we'll have some left over, okay, since we'll have some left over after we use up all of the N2, we would have 2 N2s left over. Sorry, we'd have 2 H2s left over. H2 is called the excess. Oh, I don't know why it's doing that. Okay. This is called the excess reagent. Okay, or the reagent in excess, or the reactant in excess. All right, so again, here we have our balanced reaction. Okay, now to make this table work out a little bit better and make more physical sense, what I'm going to do is I'm going to change this and add one more hydrogen molecule here. Okay, so here, if we write down the reactants here, we have 4 N2s, okay, and we have 9 H2s over in the reactants. Now, we could draw a particle model and figure out, what products we're going to make here. But let's do this without drawing the particle model first, and then let's go back and check if we've done the after reaction line correctly. Okay, so before, if we look at these reactants, we have 4 of these N2s and we have 9 of these H2s. We have 0 ammonias. Okay, so what we want to do is, before writing the particle diagram, because yeah, we could figure out what our products were using our particle diagram. But before we do that, we want to figure out this using our BCA table, because we're not always going to have a particle model to draw, and particle models are time consuming to draw. So what we want to figure out always first, and I'll write this in large letters, figure out the limiting reagent. Always, right? Whenever you're given 2 reactant amounts, we have to first figure out the limiting reagent. So we have to figure out which of these is going to be used up. So if I take a look at my nitrogen, I have 4 nitrogen molecules. If I look at the balanced reaction, I see that 1 nitrogen requires 3 hydrogens. So if I have 4 nitrogens, okay, I need 3 times that. I would need 12. So let me write this here, over here. 4 N2s requires 12 H2s. And if I look over here, I only have 9. Okay, so because I only have 9, I know that this, let me write it in red, this H2 is my limiting reagent. Okay, so I am limited by the amount of hydrogen I have. Our limiting reagent always disappears in the reaction. So I can just put in here -9 and I get 0. Remember, our change line, was used, okay, based on the limiting reagent. So now let's go back. If I use up all 9 H2s, how many N2s do I need? So I can take a look at my ratio again. For every 3 H2s, I use 1 N2. Okay, so I can either just take a third of my 9, or I can set up a proportion. I'll just take a third of my 9, right? I know that 1/3, okay, of 9, and I'll put a minus sign here, is going to equal, oops, that's going to equal 1/3 of 9 is going to equal -3. Hopefully that's not confusing to have that there. Let me write this another way, right? If I use, my top line is 1 N2 for every 3 H2. If I use 9 H2s, what's my X here? My N2s here, right, is going to be 3. My X is going to be 3. So I'll use 3 N2 particles. 4 minus 3 gives me 1 left over. Okay, now I got to figure out my product here. So my limiting reagent says that for every 3H2, I get 2 N2s, 2/3 as much. So if I take my ratio, 3H2 equals 2 NH3, and I know that I'm using 9 here, my 9H2, Solving for x, I get 6, and this would be plus 6 because this is the products. And so I get 6 NH3s. So in my particle diagram here, I should draw one leftover N2. So one N2 that does not react. Okay, and 6 NH3s. Oh, and I need to draw a few more blue circles. Forgot half of them. Okay, so there we go. Now we have a particle diagram here. Okay, and we have our leftovers and our products. And here's our particle model, and here's our BCA table. So in figuring out the limiting reactant, there are three main ways that you can figure out which thing is the limiting reactant. So I would say pick one of these ways and stick with it because, you know, just get proficient at one. As long as one works, that's all you need. You should be able to explain which thing is the limiting reactant, okay, using your calculations and words. So the first method, which we've been mostly using, is taking one reactant and using the mole ratios, the ratios in the balanced reaction, to figure out how much of the other reactant is needed and see if you have that much. If you do, then you know that you've chosen the limiting reactant. If you don't have enough of the other reactant, you know that is the limiting reactant. The other thing you can do is divide by the coefficients, divide the moles. Let me put moles here. Once you divide the moles by coefficient, you're basically normalizing, and the smaller number of moles is going to be the limiting reactant. The third way is to calculate the amount of product that you're going to form from each reactant amount. And the reactant that gives the smaller amount of product will be the limiting reactant. So any of those ways will work. You just need to pick one and stick with it. So we've been looking at particles, but moles are just like particles. They're just a collection of particles. And so the ratios that you see here with the coefficients, these ratios are particle ratios and they are mole ratios as well. They work for particles and for moles. So let's look at this reaction. This is a combustion reaction. Here, we're going to use a BCA table and answer this question: how many moles of carbon dioxide are produced? And again, here, always first determine the limiting reagent. Okay, we want to figure out what the limiting reagent is. Okay, so I'm going to put my reactants in here, 1.5 moles and 1.7 moles of the oxygen and 0 products in the beginning. My change, I've got to figure out the limiting reactant. So let me look here. If I look at my CH4 amount, I see that I have 1.5 moles of CH4. I need twice as much oxygen. If I take 2 times 1.5, I get 3 moles of oxygen. Well, I don't have 3 moles of oxygen. Okay, so that's how I know that this is my limiting reactant. Another way to do it, if that's not obvious to you, okay, if you can't seem to see how you take 1.5 times 2, I can take my mole amounts. I can take 1.5 moles of CH4 and I can divide by the coefficients. Okay, so I can divide by 1 and I get 1.5 moles of CH4. Okay, I can take my 1.7 moles of O2 and I can divide by the coefficient 2. And here I get 0.85 moles of O2. All right. Here, this is smaller. So that's how I know that this is my limiting reactant. Okay, so that's my limiting reactant. I always subtract off my entire limiting reactant to get 0 because that gets used up. Okay, I always start off with that first. Now, based on my 1.7 moles, I see that the ratio between the amount of CH4 that I use is half, right? Is half of the O2. So I can take my minus 1.7 moles and multiply by 1/2, right? I'm going to get half as many CH4 moles, 1 over 2. So that's going to be my 0.85. And then when I subtract, I end up with 0. Make sure I do my math correctly, 65 moles of CH4. That's what's going to be left over. This is my excess reactant. Okay, so now let's figure out the products. This figuring out things that have the same coefficients, like for example here, CO2 has the same ratio, same coefficient as the CH4. So whatever is used, okay, whatever amount is used for CH4, that's going to be the same amount over here for the CO2. So that's this 0.85 right here. Okay, let me put that. This is minus 0.85. Okay, here, this is going to be plus 0.85. Yep. This is plus 0.85 moles, right? Our coefficient for CO2 is the same as the coefficient for CH4. It's plus 0.85 moles. So that's 0.85. And then let's do the water, even though they didn't ask for it. Here, this coefficient for water, the same amount of water is produced as the amount of O2 used. So if I look here, I subtract, I used 1.7. So over here, I'm going to create 1.7 moles, and that's what I'll have in my products. So in my products, I end up with 0.65 moles of CH4 excess left over, I have 0.85 moles of CO2, and 1.7 moles of H2O. Okay, then I asked you to do this problem on your own. So here we have another reaction, 2SO2 plus 1O2 gives us 2 SO3s, and we want to calculate the number of moles of SO3 formed when we mix 2 moles of SO2 with 5 moles of O2 and allow it to react. So we want to set up a BCA table again. So always start off by writing down the balanced reaction. Okay, so I'm going to write this down, make my table BCA. And let me put a divider here. Okay, so here we go. We're going to start off by putting the number of moles. So SO2, oh, this should be a 2 right here. We have 2.0 moles. For the oxygen, we have 5.0 moles. And we have 0 here. So as always, need to figure out the limiting reactant. I want to look at here my ratio 2 to 1. If I use 2.0 moles of SO2, I need 1/2 times 2 moles of O2, right? 1/2, 1 over 2. So that equals 1 mole O2. Well, guess what? I've got 5 moles of O2. I have more than enough. Then enough O2. So I know that this is my excess here, and this is my limiting reagent. Okay, so now we're all set to get rid of the limiting reagent. Okay, got 0 left right there. Here, I already figured out how much O2 I need. I just need 1 mole of O2. And actually, this is the same as this ratio right here, shown in the balance reaction, because we have 2 moles, just like in the balance reaction. And then I know that these coefficients are the same, so I should produce the same amount that I used for the SO2. So plus 2.0 moles here. Okay, so I'm going to get 4 moles O2 left over, and I'm going to produce 2.0 moles of SO3. Here's another example. We'll probably do this one in class tomorrow. Here we have phosphorus and oxygen reacting. Okay, so we have P4 plus O2 gives us P4O10. Part A says balance the reaction. So the phosphorus is our balance. We got 10 oxygens. Let's put a 5 right here, and it's balanced. So here it says 0.75 moles of P4O10 and 0.5 moles of oxygen remain after reaction in a closed container. What were the initial amounts of phosphorus and oxygen? Use a BCA table. Okay, so a little bit different here, right? They're giving us the amounts left after a reaction. Okay, so let's start off by doing part B. Let's set up our table here. So P4 plus 5O2 gives us P4O10. And I'm going to set up my table right here. My B, C, and A. Divide this up. Okay, and we have to read carefully. It says 0.75 moles of P4O10 and 0.5 moles of oxygen remain after reaction. That's this after line. So let me fill this in. This is 0.75 moles. And my oxygen is 0.5 moles. And it must mean that we had 0 of the P4 left. So my P4 must be my limiting reactant, right? So let me label that there, and this is my excess. We know that from the before line, this has to be 0, right? It had to be because in the beginning we have none of it, and then we produce it. So we know that this is plus 0.75 moles. So now we can work backwards and figure out what O2 and P4 have to be, because we know that we produced this much P4O10. So looking at the ratio, we know that if we produce 0.75, okay, we need 5 times as much oxygen as P4O10. So if I take 0.75 moles times 5, okay, that's going to be, what is it going to be? 3.75. Right here. So I know that this must have been minus 3.75 moles. Okay, if that was minus 3.75 moles, what was this if I have 0.5 left over? This must be 4.25, right? 4.25 minus 3.75. I can add these together to get that. So initially I had that much. All right, so now again here, look at our coefficient. This is a 1, this is a 1. So whatever was produced here was reacted away here, so I can just fill in 0.75 moles. And to get 0 here, this had to be 0.75 moles. And so we filled in our BCA table for part B. So the initial amounts of phosphorus and oxygen, here they are. Let me circle them in red. Initially, we had this many moles of P4 and that many moles of O2. So let's write those in. So we have 0.75 moles P4 and 4.25 moles of O2. Okay, so we can go on and we can go to part C. Part C asks how many grams of phosphorus were initially present. Well, we have the moles of phosphorus. Do you remember how to change moles into grams? We use the molar mass. So our molar mass of P4 would be 4 times 30.97 grams per mole. And multiplying that out, we have 123.88 grams per mole for P4. So we take our moles times 123.88 grams per 1 mole of P4. And this will give us our grams of P4. So hopefully you're starting to see how this is going to connect to mass. Okay, once we have moles, we can connect it to mass. And really, once we can write this BCA chart for moles, we can do any stoichiometry problem that's asked for. The BCA chart will provide us with all of the answers we need, such as what's the limiting reactant, what's the excess reactant, how much of the excess reactant is left over at the end, what's produced. So the BCA table is really handy for stoichiometry problems.